There's a train sitting in a testing facility in Japan right now that has never not once touched its own track, not during a single trip, not for a single second, and this same train has already gone faster than any train in human history. 603 kilometers per hour, carrying actual passengers faster than a commercial jet during takeoff. Here's the part that should genuinely mess with your head for a second. If a train isn't touching the track, what exactly is holding it up? What's stopping hundreds of tons of steel from just crashing straight down onto the rail? The second the power cuts off, I want you to sit with that question for a moment, because the answer involves magnets cooled colder than most places in outer space. A track. That's technically also the engine. And an entire branch of engineering that spent nearly 100 years trying to prove this wasn't insane before anyone actually managed to pull it off. By the end of this video, you're going to understand exactly how something this heavy floats, why it took so long to build, and why, despite being faster and arguably safer than anything running on wheels, most of the planet still hasn't laid a single kilometer of track for it. You're also going to find out why Germany actually invented this technology, and then somehow never built it, while China quietly stole the crown. Let's start with a simple question. What actually limits how fast a normal train can go? Take a second and guess before I tell you, because most people get this wrong. It's not the engine. Modern train engines could push a train well past 350 kilometers per hour without breaking a sweat. What actually caps the speed is something far more boring. Friction, specifically the friction between a spinning steel wheel and a steel rail. At extreme speeds, that single point of contact becomes a genuine nightmare. Microscopic imperfections in the rail, the kind you'd never notice just walking across the track, start creating violent vibration once you're moving fast enough. The wheels wear down faster, the rail wears unevenly underneath them, and there's a specific phenomenon engineers call wheel-rail resonance, where those vibrations don't just stay the same, they build on themselves, getting worse and worse the longer they continue. Think of pushing a kid on a swing at exactly the right rhythm. Every push sends them higher instead of the swing just settling back down. Push a train too far past its design speed, and that same kind of resonance builds fast enough to crack a rail or destroy a wheel in a matter of minutes. Engineers have actually pushed conventional wheeled trains close to 600 kilometers per hour before, in short, heavily controlled test runs. Every single time the wheels and the rail showed catastrophic wear almost immediately afterward, great for a headline, completely useless for running actual passengers to work every morning. So back in the early 1900s, decades before anyone had the technology to actually build this, engineers started asking a much stranger question. What if you just got rid of the wheels? Here's a quick question for you. Have you ever pushed two magnets together the wrong way, same pole against same pole, and felt them shove back against your hand like they're annoyed at you? That resistance, that invisible force pushing back, is basically the entire secret behind how these trains stay in the air. Maglev, short for magnetic levitation, works by lining both the train and the track underneath it with powerful electromagnets, arranged so they repel each other. That repulsion is strong enough to lift the entire weight of the train and hold it floating, usually somewhere between 1 and 10 centimeters off the surface, depending on which system you're looking at, but floating alone doesn't get you anywhere. A train hovering perfectly still all day isn't transportation. It's just an expensive party trick. So how does it actually move forward? The track itself is lined with a series of electromagnetic coils, and by switching their polarity in a very precise rapid sequence, engineers create what's essentially a moving magnetic wave traveling down the length of the track. The train chases that wave the entire trip. It's the same basic idea as a normal electric motor, except instead of spinning in a circle the way a motor usually does, it's been unrolled flat and stretched out across the entire route. The track isn't just a track anymore, it's the motor. The train is just the piece being dragged along inside it. Once you actually see it laid out like that, it sounds almost too simple. Getting it to actually work reliably at 600 kilometers an hour with real paying passengers on board took engineers most of a century to pull off. Let's talk numbers, because I think you need to hear exactly how far this technology has already gone. That record run in Japan back in April 2015, 603 kilometers per hour, remains the fastest any train has ever traveled in recorded history, wheels or no wheels. For comparison, commercial airplanes typically cruise around 900 kilometers per hour, but they're only moving around 250 to 300 kilometers per hour during takeoff. This train on the ground was moving almost twice as fast as a jumbo jet leaving the runway. Japan's system called SCMaglev uses something called superconducting magnets, which is a genuinely more advanced version of the basic concept we just talked about. These aren't ordinary electromagnets, they're cooled down to temperatures close to absolute zero using liquid helium. At those temperatures, the electrical resistance inside the magnet coils basically disappears, letting them produce magnetic fields far stronger than a normal electromagnet could ever manage without melting itself from its own heat. So just to recap what's actually happening here, you've got a system running near absolute zero, generating one of the strongest controlled magnetic fields on the planet, lifting a multi-hundred-ton train clean off the ground and doing it reliably enough that Japan is now spending over $60 billion building an entire commercial rail line around it connecting Tokyo and Nagoya. Now here's a fair question. If this technology is genuinely this good, why isn't every country on Earth already building it? Why is nearly the whole planet still laying conventional rail for its newest high-speed projects, when something clearly faster and clearly safer already exists and has already been proven? The honest answer starts with money, and we're talking about a genuinely absurd amount of it. A Maglev guideway isn't built like a normal railway, where you're working with standardized steel rail and concrete ties that have been mass-produced. For over a century, every section of Maglev track is a custom-engineered structure that has to be built with extreme precision along its entire length, because the electromagnetic system needs extremely tight tolerances to actually function at speed. You can't just lay it down roughly and adjust later the way conventional rail crews sometimes can. Japan's Chuo Shinkansen line has a projected construction cost north of $60 billion for roughly 286 kilometers of track. Do the math on that for a second. That works out to more than $200 million for every single kilometer. Conventional high-speed rail usually costs somewhere between a fifth and a tenth of that per kilometer, depending on the terrain. A big chunk of that cost comes from something most people never think about. A huge portion of Japan's line runs underground, or straight through mountains. Because Japan's dense population and mountainous geography leave almost no available flat corridor for a straight high-speed route, tunneling through solid rock to the level of precision Maglev demands is extraordinarily expensive, and this project includes dozens of kilometers of exactly that. China took a genuinely different approach, and honestly, this is where the story gets even more interesting. Shanghai has been running a commercial Maglev line since 2004, connecting Pudong International Airport to the edge of the city. About 30 kilometers covered in roughly 8 minutes, hitting a top speed of 431 kilometers per hour. That makes it still today the fastest commercially operating train anywhere on the planet, carrying regular paying passengers, not just running in a test lab somewhere. Here's a detail almost everyone gets wrong though. Shanghai's system doesn't actually use the same technology Japan uses. Instead of superconducting magnets, it runs on conventional electromagnets in a design called electromagnetic suspension, originally developed in Germany by a company called Transrapid, and instead of floating above its guideway the way Japan's train does, it actually wraps around the track from underneath, using magnetic attraction instead of repulsion to hold itself in a stable position. Just below the structure it's clinging to. Picture the difference for a second. Japan's train gets pushed up in a way like two magnets repelling each other. China's train gets pulled up toward the track from below like two magnets attracting, carefully balanced so it never actually touches the thing it's wrapped around. Two completely different engineering answers to the exact same problem, and both of them landed on frictionless travel at extreme speed. And here's the slightly embarrassing twist in this story. Germany invented the core technology running Shanghai's train. Then Germany never actually built a commercial line with it. They developed Transrapid and proved it worked in test conditions for decades. Planned a line connecting Munich's airport to the city center, and then canceled the whole thing in 2008 because the projected cost had ballooned way past the original budget. So China essentially licensed Germany's own invention, built it commercially, and has been running it successfully for 2 decades. While the country that invented it has exactly 0 kilometers of Maglev track anywhere within its own borders. If that doesn't feel like a plot twist, I don't know what does. So why hasn't any of this spread further? Cost is a massive part of it, obviously. But there's a second problem almost nobody outside the industry ever talks about: compatibility. A Maglev line cannot connect to a conventional rail network at all, 0 exceptions. A regular train physically cannot run on a Maglev guideway, and a Maglev train physically cannot run on regular rail. Every single Maglev line has to exist as its own completely isolated system, separate stations and separate maintenance depots. No ability whatsoever to plug into the rail network a country has already spent 100 years building. That creates a genuinely brutal economic problem. Conventional high-speed rail, expensive as it already is, can at least tie into infrastructure that already exists in some places. Letting passengers transfer between high-speed and regional service without switching systems entirely. Maglev offers none of that. Every project starts from absolute zero as its own isolated island, carrying all the cost that implies and none of the network benefit that makes conventional rail an easier sell to whoever's approving. The budget. There's also a maintenance reality that caught a lot of early Maglev supporters off guard. You'd assume getting rid of wheels and friction would make upkeep dramatically simpler, and in a few specific ways it genuinely does. No wheel wear and no traditional brake pad replacement and no rail contact slowly grinding itself down. But the electromagnetic systems, especially Japan's superconducting magnets, need highly specialized maintenance involving cryogenic cooling equipment that has to run constantly to hold those extreme low temperatures. Let that cooling system fail even briefly, and the superconducting magnets lose their special properties almost instantly, and the whole levitation system just stops. That means Maglev infrastructure needs a completely different category of technician than conventional rail, and building that specialized workforce from scratch is its own long, expensive project for any country trying this for the first time. Now let's talk about safety for a second, because this is genuinely one of the more surprising parts of the whole system. Once you understand how it actually works, you'd probably assume a train floating with zero physical connection to its track would be less safe than a conventional train where the wheels are physically locked onto the rail by sheer weight. More contact should mean more stability, right? That seems like common sense. It's almost the exact opposite. Maglev guideways are built to physically wrap around or enclose the train from multiple sides, not just support it from underneath the way a normal railway does. Both the Japanese system and the German-derived Chinese system extend their track structure up along the sides of the train, meaning the magnetic forces holding it in place are working in several directions at once. Not just lifting it, but actively centering it left and right inside the channel it's riding in. Derailment in the traditional sense of a train physically coming off its track is essentially impossible under normal operation, because the train was never balanced on top of something it could slip off of in the first place. It's locked into a channel that surrounds it from every side. Getting rid of the wheels, the exact thing that sounds like it should make everything less stable, actually gave engineers the freedom to build a fundamentally more secure system than conventional rail could ever manage. Simply because they weren't boxed in anymore by the physical limits of a wheel sitting on top of a rail. There's a bigger shift happening right now that's worth mentioning, because it's actively reshaping how a handful of countries are thinking about ground transportation. China isn't stopping at Shanghai. In 2021, they unveiled a prototype Maglev train named at eventually hitting 600 kilometers per hour in regular commercial service, using an evolved version of the same electromagnetic suspension technology already proven in Shanghai, putting it in direct competition with Japan's superconducting approach even further. Out several research programs, mostly in China, are actively experimenting with vacuum tube Maglev, sometimes grouped under Hyperloop-style branding, where a Maglev train runs through a sealed tube with most of the air pumped out, cutting air resistance almost down to nothing. Without air fighting against the train engineers project, these systems could eventually push well past 1,000 kilometers per hour, edging toward the speed of sound, all while the train still never physically touches anything around it. This is still mostly experimental, probably years or even decades away from carrying an actual passenger. But the underlying physics has already been demonstrated at smaller scale in test environments. So let's bring this all the way back to where we started. A train weighing hundreds of tons carrying real passengers, moving faster than a commercial jet during takeoff, with zero physical contact between it and the ground beneath it, held up and pushed forward entirely by carefully controlled magnetic fields, some of them generated by magnets cooled to nearly absolute zero. This isn't a concept render sitting in a PowerPoint somewhere. It's already been built, it already holds the world speed record, and it's already carrying paying commuters to the airport every single day in Shanghai, with a far more ambitious version currently under construction across Japan. The reason it hasn't taken over the world yet has almost nothing to do with whether it actually works. It clearly works, and in several measurable ways it works better than the wheeled trains most of us grew up riding. The real barrier is the genuinely staggering upfront cost of building completely isolated ultra-precision infrastructure from the ground up, combined with the simple fact that it can't lean on any of the rail networks countries have already spent over a century constructing. As construction costs for regular infrastructure keep climbing, and as more countries face pressure to offer real high-speed ground alternatives instead of short domestic flights, that economic math might keep shifting further in Maglev's favor. And if it does, don't be surprised if the next country to build one isn't Japan or China at all, but somewhere nobody's currently betting on. Next time you're sitting on a regular train feeling the small vibration of the wheels bumping over every joint in the rail beneath you, it's worth remembering there's a train parked in a maintenance facility in Japan right now that has genuinely never once touched its own track during operation, capable of outrunning a jet on takeoff, floating the entire way. Held up by magnets cold enough to make liquid helium boil. That's not science fiction, and it's not staying locked in a lab somewhere. It's already running, it already broke the record, and it's probably coming to more of the world a lot sooner than most people currently expect. If this changed the way you think about what's actually possible on the ground, subscribe to Valnor. There's a lot more of this kind of hidden engineering still to dig into, and honestly this one barely scratches the surface of what happens once you stop assuming a wheel is the only way to get anywhere fast.